Okay, so hello everyone. Thanks a lot for joining today for our inaugural seminar on the learning enabled multi-agent systems. It's our great pleasure to have Professor Maryam Kamgarpour from EPFL. Her research focuses on how multi-agent systems can make safe and intelligent decisions in uncertain and dynamic environments. And in this process, she develops algorithms for safe stochastic control, reinforcement learning, game theory, and mechanism design. All of these topics are kind of very key foundations, which we hope this seminar brings forward. And it's a very great pleasure to have a speaker like Mariam as a first speaker for this series. Her contributions has been recognized with the awards from NASA, EU Starting Grant, IEEE Transactions on Control of Network Systems Outstanding Paper Award, and more recently, 2024 European Control Award. So please join me in welcoming Mariam for the series. And Mariam, the floor is yours.
Okay, thanks very much,
Do
Jimmy,
we
for
give,
the way.
do we give Claire 30 seconds to add?
No, just welcome, Maryam. It's great to see you. Maryam was a PhD student here. In fact, she and Anita Tsani were my first Berkeley PhD students that I met when I arrived at Berkeley for Stanford. And she's had a wonderful trajectory since she graduated, as you've heard. Welcome, Maryam. Sorry you couldn't be here in person. We totally understand.
Thank you very much. So thanks very much for this kind invitation, Jimmy, Claire, Shankar. It's actually a great pleasure to see you. I am very grateful for Claire for being her PhD student, as I learned a lot. And it's I often think now that I'm professor about how Claire handled things so perfectly. So she's been a great role model. So thank you. And it's a pleasure to be in this seminar series. And I would like to start with some motivation about my research. So just okay. So the talk will focus on multi-agent learning and control. So multi-agent, there are many applications that we work on. There's shared decision making in them. For example, in autonomous driving here, you see an autonomous car being extremely sort of conservative, doing the merge maneuver, because it's not perfectly accounting for how the nearby cars might react to the decisions. And this autonomous driving is a great example of multi-agent decision making, where when cars can account for others' goals, then they can make more efficient decisions. Another example that another application that drives my research is smart power grid. So here, as we liberalize the markets, we have a large number of distributed resources, batteries, electric vehicles that are participating in helping balance supply and demand of electricity. We have dynamics from the batteries, from the prosumers, and a lot of uncertainties from the renewables. And all of these players are bidding in the markets, in these markets, and we want to ensure that so they're optimizing their own local benefits, and despite this, we want to also make sure that we have a global grid that's efficient, safe, and efficient. A more recent application that I have been working on collaborating is multi-robot construction. So here our goal is to use robots to work with unprocessed and raw material to build buildings. And this is, again, the multi-agent interaction arises here. How do robots coordinate with each other? And how do they come up with creative structures? And so we are developing also multi-agent reinforcement learning towards this. In all of this, so my research focuses on developing algorithms that have provable guarantees, because the applications that we look at are safety critical. And the way I address these problems is by sort of building bridges between the stochastic control, learning theory, and game theory. And Sycamore is the name of my lab. It stands for Systems Control and Multi-Agent Optimization Research. And we are sit at this intersection, and we try to build on these, build advances in these fields to contribute to algorithms for trustworthy automation in engineering applications. Okay, so with this introduction, I want to get...
Maria, nice
yes.
name. Sycamore, great name. Did ChatGPT generate it or you generated it all by yourself?
Oh, it's all by, this talk doesn't have ChatGPT.
Sycamore, the word sycamore, great.
Thank you. Thank you. So, okay, so we multi-agent system, let's start formalizing this. So we have n agents, agent I's action is shown by AI, and the joint action is with boldface A, which is AI, and A negative I denotes actions of agents other than I. And each agent has an objective, JI, which is a function of AI, and A negative I. And so we have a set of n objectives, and for example, we are in driving, each agent wants to progress as fast as possible towards their goal. They each have a goal without colliding with other agents. In smart grid, each agent wants to minimize its electricity bill, but the price of electricity depends on the production and consumption of all the other agents. So there is coupling in their objective functions. And so because there is no single objective, we cannot talk about a single optimal solution, and we would like to look at how could agents make optimal decisions in this case. And in particular, in this talk, we want to focus on the case that where agents I does not know JI but can query it. So from her perspective, this JI is like a black box, and she can submit an AI and then observe the JI of AI A negative I. As an example, because congestion of the road to each car may not be a priori, it depends on what routes other cars have chosen and is a priori unknown to the given car I. But this car can drive, can repeatedly drive to her destination and measure, evaluate her travel time. So she can have the zero-order evaluation of her objective function, and based on this, each agent wants to learn how to optimize this decision. Similarly, the price function, the price of electricity, is generally a complex function of consumption and production, and the agent might not be able to explicitly model it, but after making some consumption and production, she can see her electricity bill and then decide to update her actions. So this is the setting we are looking at, and in the talk I'm going to talk about learning Nash equilibria in static games, and I'm going to focus on what algorithms for learning with bandit feedback, which I will clarify, and I talk about convex games and convergence conditions. Then I'm going to, for dynamic games, I'm going to talk about no regret learning and highlight some specific challenges that arise in these dynamic games, and talk about our no regret learning approach and how we used it to develop a model-based multi-agent RL, and then with some conclusions. Okay, so let's get started. First, with the notion of Nash equilibrium. So this is all known to this audience, but I just briefly formalize. So agent I's action set is capital AI, and A star is an equilibrium if for every agent JI evaluated at A star negative I is less than or equal to JI evaluated at any other AI in the feasible action set of agent I. So no agent has incentive to unilaterally deviate from her A star I, and that's why it's an equilibrium. Just as a simple example, two cars driving at an intersection, and let's say they want to progress towards the other side of their lane intersection, and if one of the cars stops and the other one goes, this is an equilibrium. But if both of them go, they get into a collision, they have a high cost, it's not an equilibrium. And if both of them stop, it's also not an equilibrium, because one of them could deviate from this and go and progress. Okay, but even in this simple example, you see that games are very interesting, because with just two actions and two agents, we can have multiple equilibria, and each of the equilibria has also a different value for each of the players. Okay, so but let's now give a little bit more structure to our games so that we can talk about the existence of equilibria and also their computation and learning. So now we're going to assume that we are in a convex game setting, which means that Ji is convex in AI given actions of others, and we also assume it's a continuously differentiable function, and this action set of AI is convex and compact. As an example, any mixed strategy extension of a finite action game is a convex game because the decision space will be a simplex for it, which is convex and compact for each player. And also, when you have a finite action game and look at the expected value, when you take mixed strategy extension of expected value of cost of each player, you get a function that's linear in player I's action when you fix others' actions, and so it's convex. But there are also other examples, like in traffic networks, you can model the travel times as a convex function of the congestion, or in electricity markets, you can model the price function as a linear function of total demand, and then the electricity bill, the cost of each player becomes a convex function of her decision variable. There are several other examples also in communication networks and so on. So this is a class of games that, so a star being a Nash equilibrium in this class of games is guaranteed to exist. And the idea of the proof here is to consider that a Nash equilibrium is a fixed point of a best response map, and you can show that under this convexity condition of the game, this best response map has a fixed point. And furthermore, in this case, the Nash equilibrium is characterized by player-wise gradients of the cost function. So if we have an unconstrained setting, for example, if you set the gradient of each player's cost with respect to her action to 0, you are at a Nash equilibrium. So this is a stationary point. You get a stationary point that's a Nash equilibrium. And if you're in a constrained setting, then you have also a first-order characterization that the gradient of each player's cost with respect to her actions transpose AI, any feasible action minus the SRI has to be, this inner product has to be non-negative. Okay. So in a convex game, we can have a first order characterization of Nash equilibria. Okay, and now we know its existence, we know that we can characterize them, and now we're going to look at, learning. How our goal is to find a decentralized learning approach. The simplest one can be a decentralized projected gradient descent. So agent I at time t, iteration t plus 1, her action is projection onto AI of on her action set of AIT minus eta t, some step size, times gradient of AI, estimate of her gradient of her cost function with respect to her decision variables. Okay. And so now what are some challenges? What I want to highlight is a couple of differences and challenges compared to single agent setting. And one is that how can agent I estimate her local gradient without access to other agents' actions? Because this function depends on actions of all the agents. And then look at conditions that such a player-wise decentralized projected gradient descent would converge. Are there any questions so far? Okay.
I'm monitoring the chat, so nothing so far.
Okay, so the first thing, I'm going to first talk about this gradient estimation. So we said that our setting is that player I does not know Ji, but she can query it. Okay, and then the natural way to estimate gradient when we can query a function is by using finite difference, right? So you query your function at AI and then at AI plus delta and try to then estimate the gradient. The challenge here is that because this function depends on other players' actions, the other players have to keep their actions fixed so that you can estimate this gradient. And this we don't necessarily want to coordinate with other players. So we want to estimate the gradient with a 1-point feedback, and this is also called like a bandit feedback in optimization literature. So the idea is that because the next time player I queries the function with the same action, others' actions might have changed, and this means that if her cost goes down, it's not clear whether it was her choice or others' choice. So we don't want to use 2-point query because it will require other agents sticking to their actions. So then the question is, how can we estimate gradients using only one query point? And so here we take inspiration from bandit optimization literature, and the idea here is that we query a randomized point, so we can sample delta from, for example, a normal distribution, and agent I now queries her function at AI plus delta, and it turns out that if you scale this ji that she receives, this zero order feedback, by delta over sigma, on average, so in expectation, you get an approximation of gradient of ji with respect to AI. But this approximation has a bias of order sigma and a variance of order 1 over sigma squared. Okay, so this is something that we can estimate the gradient with 1 point, but we get some estimate that has these properties, and so we have to account for them in our algorithm, in our step size design. Okay, so then this is
there's a
yes
question in the chat from
okay,
Adam,
sure.
who's asking, could you instead consider an approach like SPSA and perturb all action at once?
So here we are, so each agent is perturbing, because they're simultaneously doing projected approximate gradient descent. So each of the agents simultaneously is perturbing their actions. So it is like a SPSA approach, and there are different ways you can sample from the sphere, or you can sample from Gaussian distribution. There are different ways to do it, but yeah, you can think of it as this approach. Does it help answer your question?
Yeah, I think so.
Independently sampling they're independently sampling from in this case, let's say a normal distribution, perturbing the action that they wanted to query with this sample, and then by using this, by scaling that action, but by the noise, this delta divided by sigma, they get an estimate of their local gradient at that at AI. Okay, and that's a SPSA approach. So the only difference so far between this multi-agent or the additional challenge in a single agent, if it was a single agent optimization, you could query your function multiple times, and you could get rid of, for example, the variance that is growing with 1 over sigma squared, because if you have 2-point feedback, then you will not have this issue. So this is one of the differences. Then I want to talk about then another difference. So now this is, let's even drop the constraint set, but just write these update rules of all the agents, so we stack their actions together. And so here this becomes our update rule, and so each of these agents is choosing gradient of ji with respect to ai in her local gradient update. And so what we get in this case is a mapping M, which generally is not a gradient mapping, because there may not be a single function whose gradient equals to these stacked gradients of player i's local gradients. Okay, and for this reason, this M is also referred to as a pseudo gradient. As an example, if you think of a zero-sum game, a J1 of A is equal to A1, A2, which is negative of J2 of A. So this is a convex game because it's a linear, fixing the action of others, you have a linear function in the agent's action. And if you then stack these gradients, then you get this mapping, which we know that it cannot be a gradient of a single function, because if it were this, this matrix would have to be symmetric. Okay, and so this, from this also generally player-wise convexity may not be sufficient for convergence of this gradient descent type algorithm, and we need a stronger condition. So I'm going to talk about a couple of conditions. The first condition that we looked at was this, that the mapping M is strongly monotone. So which means that there exists some nu greater than 0 such that the inner product of MA minus MA prime with A minus A prime greater than or equal to nu 2 norm of A minus A prime squared for every A prime. And so a test, if you think of if the cost functions were quadratic, then you could look at this, when you look at this pseudo gradient, you would get a linear mapping, and then you can look at this, the Jacobian, and you could look at whether that is a positive definite, or if it's a positive definite matrix, you have this strong monotonicity. And generally, for general, also if it's not also quadratic, you still require positive definiteness of the Jacobian of this M at every point. Okay, so this was the original condition, but I'm going to give you another sufficient condition, and we will see in the convergence proof why, which much later we realize, is that the equilibrium is a so-called strongly variationally stable, which means that there exists a nu such that M of A transpose A minus A star is greater than or equal to nu A minus A star squared. And this strictly includes the class of strongly monotone games. And there are examples where the game is not monotone, but the equilibrium is strongly variationally stable. So this is another structural condition on the entire game, but it's a property of the equilibrium. And if now, so this is now, let's write our update rule for each player. AI t plus 1 is projection onto AI of AI t minus eta t, and this is their estimate of their local gradient using this 1-point feedback. And so together, once we stack this together, we get an estimate of the pseudo gradient. And then our kind of latest result, or the relaxed condition, was if M is Lipschitz and A star is strongly variationally stable, then you can have a step size schedule such that it's not summable, but the step size square divided by the variance square is summable, and AT would converge to A star almost surely. And the idea of the proof is to look at this Lyapunov function of AT plus 1 minus A star norm squared in expectation, and you show that this is almost decreasing. So this is less than or equal to AT minus A star squared plus an additional term that comes from the estimation of this pseudo gradient, but its order is eta t sigma t plus eta t squared over sigma t squared, and then you can see that why we need this summability condition. And then you also get an additional term minus, this is the step size M of eta t transpose AT minus A star, and we get that by strong variational stability. This is a positive term, and then there is some result, the old result going back to past work that shows that if you have a sequence of random variables that have this property, then you have this convergence. So basically,
Maryam, just going back to the zero sum, 2 versus zero sum. So strongly monotone, it doesn't include.
No, it doesn't include. I come to I have zero sum as a background slide, but I will talk. I will talk about it. So this doesn't include zero sum, and for zero sum we include a regularization. That's kind of the short story of it. But
I don't know if you know that, with this work with Lillian and Eric.
Yes.
We had some, so this convergence is a big problem, and I'm glad the gradient does converge, so it's great. So let me understand, M is, we had this thing called symplectic, they made up this fancy term about trying to fix the convergence locally, but you want to do things. These are global, is it? These are global.
It's global, but it's assuming that this M is a strongly monotone. Well, either M is a strongly monotone, or here A star, the equilibrium is strongly variationally stable, but it's a global convergence.
Interesting. Interesting. So, how do you understand monotone? Monotone means.
Okay, let me
And
just
being
go
monotone.
back.
Yeah, you're going to tell us. Okay.
Somehow I
keep going.
cannot go. How can I?
No, keep going.
Monotone would be that this eta, this would just be greater than or equal to 0. And zero-sum game would be monotone. A convex concave zero-sum game would be monotone, but not strongly monotone.
I see. Okay.
So here, if you look at, this was my example of zero-sum game. And then do you see that this is positive semi-definite, but not positive definite? Actually, if you take this inner product, you would get 0 everywhere for this, with this M. If you take this inner product, you would get 0 everywhere. It's called null monotone in that case.
Yeah.
Does that help clarify? So this is M is the stacked gradients of each players. It's a pseudo gradient, and we can look at its properties as this vector field if it is strongly monotone. We have convergence, or if the equilibrium has this strong variational stability. But okay, so under this standing assumption of player-wise convexity, I just try to summarize when do we have convergence. Strongly monotone and strongly variational stable equilibrium is basically with this proof that I showed just now. We can have that gradient descent converges. If we just have monotone, which includes zero-sum games, then we would need to do more. Gradient descent might cycle, and again, you can, if you look at this, you can imagine why gradient descent, and then you look at the continuous time dynamics, so it takes this step size. Write this as A dot equals to basically this dynamics. You see that y gradient descent would cycle. So what the remedy for that is adding some regularization or using many other methods that have been developed, like extra gradient or optimistic gradient descent or 2-time scale and so on. And then another class of games that we would have convergence is if potential, which means that this pseudo gradient is equal to gradient of some cost function j. Okay, and in this case, gradient descent would also converge. So this is the class of games that I know, like we know so far, that gradient descent type algorithms would converge. And if there is time, I can also talk about how we handle this, how we do the regularization for just merely monotone and not a strongly monotone. I can come back to it. Right, so this is, we also looked at, so I talked about variational stable equilibrium. Over the past few years, we also looked at deriving convergence rates, and also another class of games that we have been focusing on is games with coupling constraints. Again, due to time, I will not go through these, but I am happy to talk about them. So if we have these strongly monotone games and they have some coupling constraints between their actions, then we can also have a gradient descent type algorithm that would converge under some conditions on these coupling constraints. But many games, such as Markov games, do not in general satisfy these convergence conditions. And so I want to talk a little bit about Markov games, but I just pause to see if there are any questions?
But these all have this underlying assumption that you started with, right? Which is convexity or player-wise convexity.
Exactly. We started with player-wise convexity would be a standing assumption, and the reason is that actually the reason is twofold. One is that we know an equilibrium exists, so if we don't have player-wise convexity, we may not even know existence, because this existence results goes through the Kakutani fixed point theorem, which is for the best response maps, which requires the convexity of the action sets and the mapping, each player's mapping. So first existence might not we would have to develop some other tool to prove existence. And second, we don't have a first order characterization of Nash equilibria. So this gives us also the fact that first order information is sufficient, is necessary and sufficient for determining if a point is a Nash equilibrium. And that's why these our gradient descent type algorithms converge. But maybe a key thing to highlight is player-wise convexity is not enough for convergence. It's enough for existence, but for convergence we need more. Basically, this vector field, these stack gradients need to have some structure together. So either monotonicity or they should come from a gradient of a vector field.
Thank you.
You're welcome.
Yeah, of course, you know, in that was the first order condition. You know, the Hessian condition, if it exists, if it's in the interior unconstrained, you know,
Yes.
that would need something. You know, it's not adequate. You have some monotonicity, as you said. You could just have this 0, 1, -1, you know, the Hamiltonian form.
Yes, Hamiltonian.
So you have to have something on the diagonal terms, even
Exactly.
for local, even for local stability.
Yeah.
So,
Yes, you're right.
Yeah,
Exactly.
so-
Yes. Yes. Okay. So I want to talk about Markov games, and this is so let me just formalize them. So here we have the dynamics, and I'm writing it as a stochastic multi-agent dynamical system. So SH plus 1 is a sample of the probability distribution that's on the states, which is a function of state at time h, and actions of all the agents, and S0 is some initial distribution. And then we're looking at policy of agent I, pi I, which is a map from S to, so let's say here I'm just setting things up for the finite state and action setting. So it's a simplex on the set of finite actions of agent I. So S mapping to simplex of AI. And then let's consider for example, infinite horizon discounted case. So cost of each agent depends on her policy and policy of the other agents. And it's we can to make this series summable, we can have a discount factor alpha to the power of h, and then ci is the stage cost as a function of sh, and a policy of each agent evaluated at sh. And then we call just the Nash equilibrium definition always remains the same. So pi star, a set of joint policies, is Nash equilibrium if no player can change her policy and get a better cost. And the existence, so here now we are considering Markov stationary policies, randomized Markov stationary policies, and the existence of a Nash equilibrium in this class was first proven by Shapley for zero-sum Markov games, and they actually call it the stochastic games in the math literature, and then generalized to n-player general sum games in these two works. So we know that Nash equilibria exists. And so now if we think of the learning in, right, so there is also in zero-sum, at least in a class of games such as zero-sum games or potential games, they can also be computed. Now let's talk about the learning. We go to the learning setting. So we assume that, so here now we assume that it's, we don't know the dynamics of the system. It's like a black box for us. And let's say that we can parameterize this policy with some parameter theta I. So now we're looking at functions parameterized, and theta I is our parameter, and we can ask the question, let's find this equilibrium parameters through interacting with the system. So players submit their policies, and then the state evolves according to this transition dynamics, and we get a sequence of states and actions, and we want to now update these parameters. And so this is the reinforcement learning this would be the multi-agent reinforcement, one way to do the reinforcement learning approach. So so in single agent RL, now if we just have one agent and we do this gradient descent type update on the parameters, there's many works that have looked at convergence conditions of this class of policy gradient algorithms. Like this boils down to a policy gradient algorithm. So if this theta, if you have finite state and actions, and theta is parameterizing a policy such as softmax policy or so on, this becomes like a policy gradient, okay? Or theta, or your policy could be parameterized in different ways. You can have direct policy parameterization or softmax or neural softmax and so on. But the class of algorithms that this gradient descent will give us is policy gradient, and their convergence conditions. There are convergence conditions, and they're relatively well understood. But in multi-agent setting, then this same class of algorithms are generally non-convergent. So I want to, and there's been, of course, a lot of works that looked at that. I want to give a little bit of intuition or our understanding of this. So then the insight that we get from single player Markov decision processes is that we have this player-wise convexity. So we have a convex-like structure, meaning this is referred to as gradient dominance. Okay, so this in single agent RL, we know that under certain policy parameterizations, we have this approximate gradient dominance, and that's why policy gradient converges in single agent RL. And the same property helps us to have convergence for subclasses of Markov games, for example, finite horizon linear quadratic games, finite state and action potential games, and zero-sum Markov games. And I'm sorry, I only cite, like the literature is growing very fast, and I only cite some of these works. But for these classes of games, using this, mainly this property, the policy gradient algorithms have been shown to converge. But for more general classes, computation and learning of Nash equilibria is intractable. And it's not very surprising because of, even in normal form games, we know that unless we have structures such as zero-sum, potential, or monotone games, learning computing equilibrium, even in two-player case, is intractable. But this intractability, and this is the work that goes in normal form games, goes back to Daskalakis and Papadimitriou in 2008. But the exact complexity class was for Markov games was characterized in also in this work, and the intractability was clarified. I want to also give, these were some of our motivations that give some connections to, because I come from a control background, and we usually understand things through the lens of linear quadratic setting. So here again, in single agent setting, when we have a one cost function, and we have linear dynamics, and we know that linear policies are optimal, so we can parameterize our policy with as a linear function. And we know that this policy gradient, so with the gradient descent that I showed you, would have global convergence. But in the multi-agent setting, on the other hand, even in this linear quadratic setting, as soon as we have multiple players, then we don't really know we don't have convergence conditions for policy gradient. And this at the beginning was very, that kind of motivated me to understand these problems a little bit better. So we have a bit of understanding, but there's still, I think, a lot of open directions. But I give you a little bit of what we understood, at least for linear quadratic games, and then generalize. So if we just look at the scalar two-player infinite horizon LQ game, which seems very, very simple, what we showed that the Nash equilibria are a solution set of a system of third-degree polynomial in two variables. And it's hard to analyze. So what we could show is that there is at least one and at most three equilibria by just looking at, basically by talking with some friends who do algebraic geometry and trying to understand the roots of this polynomial system of equations. And what we also find out by this characterization is that it's very hard, even in linear quadratic games, to derive conditions for monotonicity, or even exist like conditions on players' cost or dynamics that give us a potential game. So this we tried to do this, and we found out that in general, the only class of potential games we could come up was the identical interest game. So all the players having the same objective, unless we basically made some assumptions such as players, the dynamics, we have n agents with decoupled dynamics and decoupled policies and so on. But on the more positive result for this scalar two-player Infinite Horizon game, we sort of we were able to come up with some convergent gradient descent algorithm by basically initializing the policy, the linear policy appropriately, and then very intricately choosing the step size based on the cost matrices, cost functions, and the dynamics. And this is kind of a recent work. But in general, it's very limited. It would be very interesting to try to understand this in more general setting, but I think it would need to understand.
What is that picture, Maryam? What's that?
This was just for when we were looking at how the number of Nash equilibria change as a function of parameters of the system.
Just to understand that, so that's the first line of the slide. So the x belongs to R2, is it? And u
x is in R, so it's a scalar. It's as simple as you can think of. But there are two players that are controlling this x.
I see. And so when u1 and u2, and then you can actually get a system of third-degree polynomials in two.
Exactly. Yes. Exactly.
And you can analyze that, and
you can look at its discriminant and then try it based on the parameters of the system, figure out and conditions on this discriminant determine how many real roots it will have, and then you are looking at roots that are also inside some interval, because you want this to be stabilizing linear policies, and then you can basically, based on this polynomial would have at most 9 roots, but you can rule out some of them and conclude that you have at least one and at most 3 equilibria.
Interesting. And this is just a count, and
it's just a count, yes. But it also tells us that we cannot have global convergence because we have generally more than one equilibrium. But we also wanted to understand whether they can be saddle or they can be locally attractive, but it's very hard to
so that's what I was going to ask. The one in the middle is not stable, and the other two are not.
So I don't remember in this case, but we would have to. It was very hard to derive analytic conditions. So far, my student, this was the most analytic. These are the most analytic things we can do, to just say how many equilibria we have, characterize them with this polynomial, and then use some algebraic geometry package to basically tell us to simplify these polynomials and look at its roots. But yeah, it's very hard to analyze more. So we have more than one equilibria generally, so we cannot have global convergence, but at the same time, we could have some convergence based on initialization for this scalar case, but we don't know how to generalize these results to multiplayer case, so there's open directions there. Okay, so this brings me to the last part, which is, what can we do?
Ask a quick clarifying question?
Yes.
So you said you have conditions on initialization.
Yes.
Does that mean that, is it possible to characterize the region of attraction?
Yes, well, but for this scalar case, that's what we did. Yes.
Okay.
Yeah.
I see.
It's a very, very recent work, and my student will present it in CDC. I'm happy to talk more about it. Yeah.
Thank you.
Okay, so we can then in general, this is even for linear quadratic games. They're hard, but we can then what do people do? We have the same challenge in normal form games, and we cannot compute equilibria beyond zero-sum potential and monotone games. So then we can consider a relaxation of equilibrium notion, and we can consider a probability distribution on the joint action of the players, and we call that a coarse-correlated equilibrium. If you sample an action in, okay, now I have theta from this distribution, from this probability distribution joint actions, then no player has incentive to deviate its action from that sample actions. And the classical example for this is, again, for these two cars, is that there can be a traffic light that with some probability gives a go to one direction and a stop to the other direction. Okay. So this is a distribution on the joint actions. It's not a product distribution like a mixed Nash equilibrium. And this is a relaxation of mixed Nash equilibrium. And we know that past work has shown that if you have a so-called no-regret algorithm, if each player runs a local no-regret algorithm, then the empirical distribution of played actions goes to a coarse-correlated distribution, and our goal, but these no-regret algorithms would not scale well if you have a very large dimensional action space. And we focused, we wanted to understand, first of all, these algorithms better and design more scalable no-regret learning algorithms. So how much time do I have, Shimei?
15 minutes.
10 to 15.
Okay, so I just try to give some a little bit of background about this, about the no-regret algorithms and how we contributed there. So if now, let's look at a no-regret problem. So a player is submitting an action, theta t, and she doesn't know the cost function in advance, but she experiences a time varying cost, let's say ji t of theta t, and she has to update this theta t in a way that she minimizes regret. So regret of player I at capital time t is the difference between her incurred costs and the cost of the best action in hindsight. So if she knew this sequence in advance and she could pick one action to optimize it, then this the difference between what she incurred and this would be her regret. Is called her regret in this online learning literature, and we call the algorithm no regret if RIT over T goes to 0. This comes from online learning literature. The connection to a game is that even though player I's cost in a static game is not changing, because others' actions at each round of playing the game are changing, she experiences a time varying cost function. Okay, because there's a part of this argument of this function that she cannot influence and without her knowledge is fixing. And it is known that if players implement a no-regret algorithm, okay, this I just said there, then we have some convergence to this relaxed notion of equilibrium. And if we have also some other more structure on the game, like zero-sum game, we also have the convergence is to a Nash equilibrium. And the rate of regret also gives us the rate of convergence, basically, to this equilibrium. And so if n is the number of actions of players and t is the number of iterations, when the players have bandit feedback, meaning that at each time they only observe their cost for their played actions, not all other actions, we know that the best regret rate that we can achieve is square root of t and log n. But if they have full feedback, meaning at each time they observe the cost for every action, not just for the played action, so then in this case, the regret grows as root t log n. So we get much improvement in terms of number of actions if they have full feedback. And it makes sense because at each round they're seeing n bits of more information. They're seeing the cost function evaluate all the actions, not just the played actions. And these, so what we wanted to look at is, can we improve the dependence on n in a game? Because, for example, if our action set still comes from a continuous domain and we're discretizing that domain, then the first one, the bandit feedback, this would imply an exponential dependence on the dimension of the action space. And generally the answer is no, because these rates match the lower bound for this type of information, but they are for online learning, and they don't account for the fact that in a game the cost function is not arbitrarily time varying. So what our idea was that, given that player i's cost variations are only due to others' actions, and it's not otherwise a time varying function, let's try to estimate this cost through the interactions and mimic the full feedback, because in the bandit feedback, okay, I think in reducing the slides, I skipped, sorry. There is a class of algorithms that achieve this, which is multiplicative weight update. So the weight of each action, the weight of action k at time t plus 1 is equal to weight of action k at time t times some exponential function of so times e to the negative eta t j of k, which is experience cost. And in the full feedback, the weight of all actions is updated because we see the cost evaluated at all actions. Okay, so this is called the multiplicative weight update algorithm, which achieves the best rates in both banded and full feedback. And now by estimating this cost, we mimic full feedback, because we can then plug in our estimate at each time and update the weight of all actions. Okay, so this is again comes from the connection of with the bandit learning literature, where you have these k actions. These actions are basically the arms, and a priori you don't know which arm which give you which reward. But by experimenting, you can learn, you can estimate this. Okay, so this is the high-level idea of our algorithm, but I'm going to give it a little bit more insight into how we do this, because we want to learn. Let me just pause and see if there are any questions. I think here I kind of skipped some things and just want to make sure that what I said.
I have one quick question.
Yes.
So in this dynamics, is it assumed you know AT minus I, or that's
That's a very good question. So this is also, we also have to assume, because to estimate this function, it has two arguments, and we have to assume not only we see the cost function value at AIT, but afterwards we also see actions of others, so that we can estimate this function.
I see. Okay.
Other questions about this setup? So maybe like I just recap. So what we want to do is we want to learn a coarse-correlated equilibrium. We know that no-regret learning converges to a coarse-correlated equilibrium. So we want a no-regret learning algorithm that scales well with number of actions. And to do that, we exploit the fact that we're in a game. We are not in an arbitrary online learning with time-varying cost functions. And we try to learn the cost functions of the players. And this work came from a collaboration with my colleagues in computer science, who use Gaussian processes for learning functions. So then because if we are to learn the function, we have to assume some modeling class for the function. So let us assume that this function, for example, comes from it has a so-called bounded norm in a reproducing kernel space, which implies it can be modeled as a Gaussian process. So the function is a sample from the space of functions with mean mu a and a covariance function. Okay, and there are different. This covariance function is something we fixed. There are different ways to do it, and the idea is that at the beginning we don't know the function. It could be, and with high confidence, the function could be any of these curves. So this is. But once we make some measurements, our uncertainty about the measured points decrease, and we learn this function better and better, but also the covariance function gives us a way to optimize the function values at nearby points. So we have some estimate of the functions, and so we basically update the posterior mean and the variance of these functions using regression based on the measurements of the function values and the arguments which we queried the function. And this, one reason to use these Gaussian process functions is that we also have confidence bounds on estimated cost. So if we take the mean and subtract some properly chosen beta t times the variance, it turns out it has been shown that then this estimated function is with high probability a lower bound of the true function, assuming the function comes from this modeling class. So then basically putting this together, then this was our Gaussian process multiplicative weight update algorithm for games where player I has this n actions, the cost is unknown, and she optimistically estimate the cost at each time. And then so then this is the weight of the actions at each iteration. She samples from the weights. She observes the experience cost and the actions of others so that she can update her cost, her optimistic estimate of the cost, and then accordingly update the weights of all the actions. Should be K. Oh, okay, A, this is the played action by other players simultaneously. And then with this, if with this construction, then we can show that if the player's cost comes from this GP prior, then the regret grows as root T log n. The main point is the dependence that was linear in n in here disappeared. And then there's an additional term, gamma t root t, which this gamma t is the amount of information you gain about the function. So it depends on the different kernels, but past work has shown that then this scales sublinearly, so you still would have a regret that goes to 0. So in summary, in a game setting, by approximating these functions, we get a better we get a regret rate that scales better with the number of actions by exploiting the fact that we're in a game, not an arbitrary online learning scenario, and the modeling assumption on the functions. And over the past years, we extended this in many ways. We applied it to contextual games, minimax games, to mechanism design, to multi-gen RL. Yeah.
Previous slide, this gamma t has to grow less than square root t, right? Because
yes, exactly. Exactly correct. And in for different kernels, it's shown that it goes.
The thing is without gamma t. Okay.
Yeah, exactly.
Okay. So all of them are less than square root t. They have to be less than square root t, right? Because for the regret, you're going to divide by t, right?
Yes, exactly. We would divide by t. Yes.
So all of them, whether it's linear.
Independent. Let me think. Independent.
I don't know what the independent. Maybe
yes, but the other ones, yes.
They're all square root t. Okay.
Yeah. The exact bounds on this are derived in this paper of Srinivas and Krause, but they are for these the kernels squared exponential matter and linear, they are less than square t. And this paper originally just looked at single player, no regret, and that's
what you're saying in that term is that if you have Gaussian priors for the player's cost, then
yes,
that you have a penalty, and that penalty is keep the
exactly
dependence on square root log n, but
yes,
then the penalty doesn't depend on n, but it depends on
Yes, exactly. Yeah, this is a penalty. So the penalty, like the bad dependence on n disappeared, but you pay the price of you're learning these functions. That's what this term is coming from, because you don't know the functions, so you don't observe full feedback. You're estimating the functions, and this shows you how well you can estimate and how fast you can estimate it with gamma t. Yeah, so it's like it's a trade-off. Yes.
So this gamma of t, does it also have a dependence on the number of agents?
No, gamma t doesn't have dependence on number of agents, because this I think like one main point of this no regret algorithm is that players are independent in a decoupled way, are running this locally. So it has
That's funny, right? I mean, none of the regrets seem to depend on the number of players.
Yeah, it doesn't depend on the number of players, correct. But J, let me just think, because J depends on actions of everybody, and this gamma T is certainly not exponential, but how does it depend on? Yeah, it is sublinear. I guess it's the same dependence. That's where on the actions of everybody, sublinear dependence. But
So, Chinmay, in your sort of bandit feedback, what was your dependence on number of players?
Independence
Yeah, I
on
think in
number of players.
a lot
Yes.
of multi-agent setting, it grows exponentially. So
No, but not in a no regret
So-
setting, right? Not in a no regret
Right.
setting, because they're independently, they're updating their strategy. But this gamma T, I mean, so let me just go back. So certainly here, you know, because this result is independent of how many others are playing. It's just for any time varying function, and only player i's number of actions come into play, right?
Yeah.
Okay, so you can see that, and this already holds for our game setting, and it implies the rate of convergence of this divided by t to the CCE. So it's independent of number of agents, convergence rate to a CCE when you run a no regret. But what I'm doing here is not completely independent, because gamma t is telling you how much information you're learning about ji, which depends on everybody's action. So that dependence is also mild, but its exact form of it, I would have to check. I thank you for the question.
Okay.
But it's
The
not
reason we're asking this is, you know, there's some paper we wrote with Chinmay actually, the lead, where we were trying to marry X3, the bandit,
Oh, okay.
with matching. And there, I think there also the regret, and that's where these regret bounds depended exponentially. And actually, the reviewers beat up on us for that. And I think Chinmay then reduced it to super. But it's still super, at least super linear. Am I saying all this right, Chinmay?
Yeah, I think we were not able to reduce it in that particular paper, but like empirically, it was much better.
But
In
I'm curious. Maybe I can discuss it more
Yeah, we'll
offline.
follow
Yeah.
up with you. We'll definitely follow up on all this.
Yeah, that would be good.
Keep going. I want to be
Okay,
sure.
I just want to say we extended it to multi-agent RL setting. So here we assume the dynamics are coming from some GP. Okay, the T, I have to drop this T, but the dynamics F are coming from some GP, and we try to basically we estimate this function by observing the trajectories and the actions of the agents. The algorithm is very, I simplify in greatly to just put it here. It's much more complicated, but the high level idea is that we estimate these, we model them as Gaussian process, and we estimate them by observing trajectory of the system and using Gaussian process regression. And this gives us an we can then come up with optimistic estimate of the JIs. Because now I'm minimizing costs, I should say a lower confidence bound. And then we compute the coarse-correlated equilibria knowing these functions, and then we play actions from this distribution and we repeat this process. This is a high level of the algorithm, idea of the algorithm. So players sample from this joint distribution, then observe the trajectories, estimate the dynamics. This is done in a central way, so it's what is called centralized training, decentralized execution. So the central unit estimates the dynamics, and then we compute coarse-correlated equilibria of these known, now it's a known game because we know the dynamics, and we repeat this process, and then under some conditions we can have a regret bound that looks like O square root of t it, and this it is like that gamma t, but for this dynamical game setting, and it's sublinear in H, the horizon. We looked at finite horizon saying n number of players and dimension of the space. So that's sort of the high level summary of the algorithm. We applied it to autonomous driving examples. So this is from SMARTS, which is an autonomous car simulation environment, and it has some multi-agent RL framework built in it. And it has realistic traffic data and car dynamics. And I just show you an example from one of the scenarios. So here is a lane emerge scenario. The pictures are from there, and I'm sorry they're not so clear, but there's a human driven car with a box around it, and there are two autonomous cars with red, and they want to maximize progress, and this car on the top wants to also change lane to human driven car lane. And so the dynamics here, so they want to progress towards the goal and avoid collision. So we have a penalty. This is not looking at constraints as hard. That's our future work. There's a penalty for collision, and there's a reward for progressing forward. The dynamics, the states are position and velocity of the cars. The AI are heading and speed. And then this policy of the cars was what was in this simulator, which was parameterized by some neural network, and we're just updating this parameter using the approach that I mentioned. And the idea here is that if these two cars can, if they look at this as a single agent scenario, they may be too conservative, but if they see that they're both trying to maximize progress, they have opportunity to coordinate and overtake the human-driven car. And that's what we observe in this case. So this is if we look at it as a single agent case, so other cars would view every other car as a moving obstacle, then each agent's reward here, agent 0, agent 1, average agent, is slightly lower than if they look at it as a multi-agent case. So if we run a multi-agent learning algorithm, so in this case, average reward and each agent's reward is a bit higher. And so in practice, what this means that the fact that they coordinate implicitly through this coarse-correlated equilibrium, it means less braking and more successful merges in front of the human-driven car. And it's also here a comparison with a model-free approach. So this is model-based because we modeled the dynamics with this Gaussian process. So to get to certain level of reward, average reward, in this model-based takes significantly less number of iterations than a model-free one, which is in black. So model-based in practice, in this case, seems to be more efficient. Okay, I think I just summarized. So, and we can take questions more after. So in the first part of the talk, I talked about if we have a convex game under some structure, what structures we can have decoupled learning algorithms that converge to a Nash equilibrium based only on function evaluations and local gradient updates. But it's difficult to extend this to Markov games. And so in Markov games, to go in that space, we started by understanding no-regret learning and coarse-correlated equilibria, and we looked at no-regret algorithm, model-based no-regret algorithms that could be more efficient in terms of number of actions of agents. And we then applied this to the multi-agent, the Markov game setting. There are many directions that I think are open and are very interesting and also challenging. So if we have safety and reachability constraints in these Markov games, so this kind of brings back with the theme that has been since my work with Claire that has stayed always with me. So how do we design algorithms that, multi-agent algorithms that can jointly satisfy this? This is very hard. Even we realize that existence and characterization of equilibria is hard in this case. And then there are other realistic settings, provable algorithms under partial and asymmetric information. I think this is very interesting because generally agents would each have asymmetric information, partial observation of the state, and it creates a lot of challenges. We know that from literature, from distributed control. Learning of good equilibria and mechanism design. So there's works in static games. Mechanism design has been really well explored, but as soon as we come to dynamic games, it's really, there are a lot of open questions in there. So are there a class of games that have good equilibria, or can we design mechanisms that converge to good equilibria? And the applications, which I motivated at the beginning, which continue to drive our work. And so I just end with acknowledgements with the PhD students and collaborators who mainly contribute to this work, my group at EPFL, and the funding. And thank you for your attention, and I'm happy to answer more questions. Thank you.
Thanks, Maryam, for the fantastic talk. Let's open the floor for